All right. Thanks, everyone, and welcome to the final network seminar of the Michaelmas term. We're glad today to have with us Clara Stegehuis, who's a professor in the Operations Research Group at University of Twente, and previously did her PhD in Networks and Communities at Eindhoven University of Technology. And she's going to talk to us today about maximal cliques, many or few. So please, Clara, take it away.
Yes, okay. Thank you very much for having me. So this talk is a joint work with Thomas Blasius and Maximilian from Karlsruhe Institute of Technology. So I think I can start with a summary of the process of this research project, and that's roughly this. So we thought we were trying to prove something very simple, but it turned out to be much more difficult than we thought. And also, actually, I couldn't find a picture which shows this, the fact that you actually don't even get to the goal you want to achieve. But we didn't make it. But I thought it's still we still do have some results, so I would like to present them today. So now about the content. So what is a maximal clique? So a maximal clique is a network that is a clique. So every node is connected to every other node, but it cannot be part of a larger clique. So in this example, there are you see two maximal cliques because the four clique is not part of any larger clique. But for example, the triangles in the four clique are not maximal cliques because there's actually a larger clique, the four clique, that also contains this triangle. And also the single node on top is also not a maximal clique because it's also contained in a two clique. So this is what a maximal clique is. And one question that is often of interest in computer science is how many maximal cliques are there in your graph in total? So for example, this particular network has two maximal cliques. But of course, if the networks become larger, you can have many more of them. And then, okay, so why would you be interested particularly in these maximal cliques? Well, if you have the maximal cliques, then you actually have all cliques in the network. So here in this example, if you have the two maximal cliques, so the two clique and the four clique, you can just get all subsets of these cliques, and they give you all cliques in the entire network. So maximal cliques give you all cliques in the network. And if you have a list of all these maximal cliques, that means that you can also compute like what is the size of the largest clique in a network, which is a difficult problem in computer science. But you can also compute things like clustering coefficients, which are based on very small cliques, or triangles. And there's also other statistics in network science that are based on cliques, closure coefficients, and you can also achieve them once you have a list of these maximal cliques. Now, of course, if you have a large network, you then first have to find this list of maximal cliques. And this is also a question that has been of interest. So how many maximal cliques are present in a given graph? So of all possible sizes. And it turns out that there's a so-called output polynomial algorithm that lists all possible maximal cliques. So what does this mean? Well, an output polynomial algorithm means that it's polynomial in the input as well as the output size. So that in this case, it means it's polynomial in the size, so the number of nodes in your network, or maybe the number of edges, but also in the number of maximal cliques that are present in the network. And then the question is this useful? And the answer is, well, that really depends. Because because usually you want to have a polynomial time algorithm, because polynomial time algorithms are reasonably fast, at least they're not exponential time. But this means that if you have a very small number of maximal cliques in your network, this output polynomial time algorithm will be able to find them very fast, because then it's polynomial in a very small number of cliques. For example, if the number of maximal cliques is linear, then if the number of maximal cliques is roughly equal to the number of vertices, then the running time would be polynomial in the number of vertices, which is okay. But the problem is that this algorithm only works if you have a small amount of maximal cliques. But you need to run the algorithm to actually count the number of maximal cliques. So this algorithm, it's a bit of a vicious cycle. So the algorithm may run very fast, but you need to run the algorithm to know if it runs very fast. So this output polynomial algorithm can be useful in some cases, but not in others. And I thought I'd just give you a brief idea of what this algorithm actually looks like. It's not super important for the rest of the talk, but I still like it very much. The first one was given by Tsukiyama in the 70s, but I think there's several refinements of this algorithm. But the main idea is that you have a specific graph, and then what you do is you keep on removing nodes, counting maximal cliques, and then adding them back basically and seeing how does this adding back this node influence the number of maximal cliques. Because there's the relation between, so suppose that you remove a specific node G. So suppose that we have one particular maximal clique, so the clique which is shaded in blue. Then what you can either have, and then what happens if you remove a node V? So here we have this clique, here we have a specific node V. If you remove this specific node V, then one thing that can happen is that your clique still remains maximal because this node V was somewhere not even close to the clique at all. Or what can of course also happen in another case. So suppose that we had a clique in the graph where the node V was removed. So we have a clique in this graph. If you add back this node V, then either this node V did not affect this clique at all, and the clique is still maximal. Or in some cases, here we have a maximal clique, which is an edge. But if I add back a specific node, then it may happen that the previous clique, of course, it will still be a clique because this edge is still a 2-clique. But when I add a new vertex, this 2-clique may not be maximal. But in that case, if it's not maximal, then it can only be maximal because this extra vertex forms a maximal clique with it. So it does mean that every clique in this graph where you remove some vertex V has at least as many maximal cliques, so that this graph has at least as many maximal cliques as this one, because everyone in this one forms a maximal clique here as well, either with an added vertex or not. And it turns out that you can also make some arguments the other way around. So suppose that I now focus on a clique in my large graph, G, then either, of course, maybe if I have a maximal clique here, either, of course, I remove a vertex all the way here, then nothing happens and it will still be maximal. But in this case, for example, if I remove this specific vertex, it can also be the case that now here I destroy my maximal clique because I removed a vertex from the clique. And then the remaining clique, so what is remaining, so we had a triangle which was a clique, and then an edge remains when you remove the vertex V. And then it's possible that now this one is not maximal anymore because here the triangle was maximal, but this edge is not a maximal clique because it's also contained in the triangle. So that means that if you remove a vertex V, then you can always form a maximal clique with the rest. If you remove this vertex V, you can always form a maximal clique with the rest, but it may not be the same. So what does all of this mean? Well, it means that, so this algorithm that counts the number of maximal cliques is a recursive algorithm. So it just removes random vertices and then starts counting maximal clique in the graph minus the vertex. And it keeps on doing so. But why does it take output polynomial time? Well, for every clique that you find somewhere over here, every time you add back the edge, you need to check, is it still a maximal clique? Or maybe my maximal clique has shifted. And then again, you add another vertex and you again have to check, is this clique maximal? Oh, in this case, maybe yes. In other cases, maybe no. So per maximal clique, it takes the number of edges times the number of vertices amount of time. So that means that in this case, because for every clique you constantly need to check this algorithm, so how fast it runs depends on the number of cliques in the system. And this is the only runs fast, of course, if you have a very low number of maximal cliques. But so in this case, for example, we only have 2 maximal cliques, so that's not so bad. But of course, so how many? So the question is, what is the worst case that can happen? What are the most maximal cliques that you can find in a graph at all? And it turns out it can get pretty bad. So for that, I just introduced a complement graph, which is basically just if you have a graph, you replace all the edges by non-edges, and all the non-edges, they become edges. So, and from that, you can then see that if you have a maximal clique in the original graph, so in this case, there's no triangle, so all maximal cliques are edges, then all maximal cliques in this graph form an independent set, which means a set with no edges between them at all, in the complement graph. So for example, this is a maximal clique here, and here it's an independent set because there's no edges between them. And the same holds for this one, and for this one. If there's any questions on this, feel free, of course, to stop me or post something in the chat. Okay, so then from this we can get to the worst case. So the worst case, I know, so that means, so if you have many maximal cliques in a graph, that means that in a complement set, you should have many independent sets, many maximal independent sets. So independent sets that cannot be made any larger. So in this case, for example, the maximum independent set here is also 2, because you cannot make a set of 3 vertices without any edges between them. Now, the worst case for having many different independent sets is actually, or maybe one of the worst cases, is this one, where you have 2k vertices and you form a matching. So you just add edges like this. And then what happens is you can choose any of the ends of any of these 2 edges, and they will form a maximal independent set. So for example, you choose this one, this one, this one, this one, this one. There's no edges between any of those in the set. So it's an independent set, and you cannot make this independent set any larger than it is now, because you then always have an edge somewhere in this set. But it means because for every edge, you can make 2 choices of which of the 2 to add in the independent set. So that means that there's 2 to the k maximal independent sets. So then this one is so this one has many maximal independent sets. So if you then go to the complement graph, which looks very messy because there's so many edges, but what it means, this is just a clique minus a matching. So it's very close to being a complete graph, but not really. And there you have 2 to the k maximal cliques. So this means, for example, that this output polynomial algorithm, so suppose that we have a graph on n vertices, this output polynomial algorithm would be polynomial in 2 to the n. And polynomial in 2 to the n is actually not a polynomial in your graph size at all. So counting the number, or like determining whether there's more than a specific number of maximal clique is actually an NP hard problem. So a very difficult problem. But that is, of course, in the worst case, because that is only actually if you make graphs that look somewhat like this. But we know that most real networks really do not look like this at all. So my co-authors actually made some experiments on this, because what they found is that this output polynomial algorithm in practice actually runs very fast, even on very large networks. So what they did is for example, here, let's focus on this one. So they tested many different real networks. So every dot in this plot is a real network. And then what they plotted was on the x-axis, something like, degree. It's not really the variance of the degrees, but some rescaled way of the variance. So what it means is, if you're all the way here, then there's a high variance in the degrees. Here it's actually very homogeneous, so most vertices have roughly the same degrees. And on the y-axis, they have something which they call locality, which means if I have an edge, so how many common neighbors? What is the fraction of common neighbors between the two ends of an average edge? So here would be so many common neighbors, so very clustered in another way. And here there would be only few, so more like a tree, basically. So every network falls somewhere on it, and the color actually represents how many maximal cliques this algorithm found, divided by the number of edges. And what is interesting is that in all these real network datasets, they did not find one single real-world network which had more maximal cliques than the number of edges. And that is interesting because we saw in the worst case, actually, you can have an exponential number of maximal cliques in your network size, basically. But here we have sparse networks, so the number of edges is roughly linear in the number of vertices, and there's only very few maximal cliques in practice. So the question that we wanted to answer is, how many maximal cliques are present in, so because probably the fact that these real-world networks have only so few maximal cliques has something to do with that they really do not look like these extreme worst-case examples. So what we wanted to ask is, so how many maximal cliques are present in basically an average graph or a typical graph? But then the question is, of course, then what do we assume that an average graph looks like? And here we just said, okay, so how many maximal cliques do we find in a specific random graph model? And then hopefully that will also be linear in the number of nodes, so that we can show that for most random graph models, we actually see a low number of maximal cliques, which would explain maybe why we also see so few of them in practice. So to determine which random graph models to use, we try to use some properties that people often study in network science. So one thing is that people often assume that networks are sort of scale-free, so that you have a power law degree distribution or something which is roughly like it. So the fraction of vertices with degree k would then follow would be approximately k to the power minus 12. So many vertices with very low degree, but also a few with very high degrees. And often, at least in mathematics, people assume that tau is in between 2 and 3, but of course you can also have different exponents of tau. And one very well-studied model that has this scale-free or power law degree distribution is the inhomogeneous random graph, sometimes also called the hidden variable model. And in that model, every vertex is a weight, and this weight is sampled from a power law distribution. And then given the weights, two vertices are connected with this specific probability, which depends on the weight. So the product of the two weights of the two vertices divided by n times mu. So the higher the weight, the more likely you are to connect to other vertices. So it just means you sample n vertices, everyone gets a weight, so some have higher weights than others. And after you sample the weights, you sample the connections. And you typically see that vertices with higher weights have more connections than vertices with very low weights. And in fact, you can actually show that for these models, the weights and the degrees are actually very close to each other. So you can also just think of the weight as being the degree of a vertex. Now, this, of course, so this power law is not everything that we see in real networks. So we also typically see in most networks that they are very clustered. And the clustering doesn't happen in this model. This model will actually look very much like a tree. And one very popular way of adding a realistic a way of getting clustered network is to add network geometry. And one model to achieve this is the geometric inhomogeneous random graph, which is roughly equivalent to the hyperbolic random graph for people who know the hyperbolic random graph. And this model works very similarly. So again, you start with vertices. Every vertex gets a weight, sampled from, again, this power law distribution. But then now, actually, you also assume that the vertices have a uniform distribution, a uniform position on some torus. So now, so previously the position of the vertices did not have any meaning, but here the positions of the vertices actually are the position of these vertices in some space. And then we connect vertices independently with probability the product of their weights, again, like before, divided by this n. But now we also divide by the distance to the power d. So that means that the smaller the distance between two nodes, the more likely they are to connect. So if you do it like this, then what you typically see is that, so there's actually two ways to be likely to form a connection. So either you have high weight, then you form connections with, you can also actually are likely to form connections with far away vertices. But vertices with low weights, they typically form most connections with vertices that are actually close by them. And because of the triangle inequality, because then if this vertex connects to this one and this one connects to this one, then these ones also must be sort of close by each other. So it's much more likely that if two neighbors of a vertex intersect as well and also connect. So we looked at these two models, and the question we asked is how many maximal cliques can you find in these random graph models? And we set out to prove that it's linear, but in fact, at the end of the week, for the model without geometry, we actually got an exponential lower bound. So the precise result that we got is something like this, but it doesn't really, so for some epsilon and some b, but the expected number of maximal cliques in an inhomogeneous random graph of size n is b to the power n to the power this thing, which we assumed that was, because we assumed that tau was between 2 and 3, this is actually positive. So b to the power n, and b is larger than 1. So this is really exponential growth of the number of maximal cliques. So it's really not linear at all. And then, unfortunately, for this geometric inhomogeneous random graph, we got a very similar result. So again, in this geometric inhomogeneous random graph, you again get this b to the power n to the power some positive exponent. So in random graphs, it seems that there's actually many maximal cliques. So why is that? So what we did, so remember that one of the worst cases for having many maximal cliques is to have a large co-matching. So a very large almost clique. So a clique where you remove only a matching. And of course, most this inhomogeneous random graph or the hyperbolic random graph or the geometric inhomogeneous random graph will not look like a clique minus matching at all. But interestingly, they still have a small part of the graph which does look like a clique minus matching. So what we actually showed that when the weights, so in this model, when the weights are approximately square root mu n, so they should not be large. So if wi and wj are both square root mu n, then the connection probability becomes 1. So when the weights become larger than square root mu n, all the vertices become a clique, which is not a clique minus matching, then it's only one maximal clique. But if they're just slightly lower than that, then you're actually quite likely to find a clique minus a matching. And then it turns out if you also have this geometry, then what can happen is that when you choose vertices, for example, in a circle like this, it's actually quite likely, because these vertices are then quite far, these ones are far, these ones are far, then it's not so unlikely that these vertices connect into almost a clique, but not to the opposite one. So they don't form an exact clique, but they form a clique minus a matching. So it turns out that also adding this geometry doesn't make things better. So maybe, so a little bit more, to be a little bit more precise. So we said that for this inhomogeneous random graph, we said that weight should be close to square mu n, but a bit smaller. So we say, suppose that vertices are square mu n, well, a half, that's also a factor, is not really important. But minus some g up until the square of mu n minus some h. And then we say, so suppose that we have the vertices here in the geometric case, so that we're in the suppose that we have one-dimensional geometry. So all vertices are positioned here just on the line. So the vertices are here. And then we say, so let's look for vertices that are in these boxes. So one vertex in this box, 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 and one vertex in this box. And what we want to show is that any set of vertices that you choose in these boxes is quite likely to form a clique minus a matching. So what we first want to show is that it's actually quite likely, if you have a vertex somewhere here, that it connects to all these other boxes, but not to this one. So we would like to show that it's quite likely that that these connections happen. And for that, we actually have to make sure that the weights are not so low. Because if the weights are too low, then you're unlikely to form a connection, and then you would maybe not connect to this one at all. And then actually, if you do it well, you can derive a relation between the gap between these boxes and what the weight should be. And then if you do it well, you can show that the connection probability between these two is actually, these ones is actually 1. But then, of course, what you also want to show is that this one is not happening, because otherwise you would have a clique, and you don't have a clique minus a matching, but you have a clique. So the weight should not be too high that you form a clique together, and that you can actually also again relate to this h, which is now the width of the box. But this I'm not going into much detail. And then, so what we showed is that if you, so in this case, you show that if you choose vertices in all these boxes, they form a clique minus matching. And then, of course, you still have to show that these boxes still are very likely to contain vertices in the first place. So that means that these boxes cannot be very small, because if they're too small, then it's quite likely that one of them will just be empty and there will not be no vertex in them, because the vertices are uniformly positioned on this one-dimensional torus. And it turns out that you have to find out so that the width of the box should be at least larger than something. And then you can see that the largest thing, so you have a lower bound, so on how many of these, so these widths should be larger than something, and so then you have a bound on the largest number of boxes that you can create, so that creates a co-clique of a specific size. And then remember before that the exponent was then, if you have a clique minus a matching of size k, we had 2 to the k maximal cliques. So then here we have a maximal clique of size n to the power something. A co-clique of size n to the power something. That means that there's 2 to the power n to the power this thing maximal cliques. So in any case, so these results basically show that it's quite bad. So even random graph models have exponential numbers of maximal cliques. So here I have some results to defend ourselves, because we thought it would be growing linearly. So here we see simulations of this geometric inhomogeneous random graph in orange, blue, and green. And a graph without geometry, so the yellow one, that was the inhomogeneous random graph, so that is the yellow one. And we counted here the number of maximal cliques on weights which are close to square root n, because we saw in the proof that that is where most of them are. And we have different exponents for the degree. And you can see, for example, if your degree exponent is actually close to 3, so that if the power law is not very strong, then here we have many vertices, so 100k, 100 million, and here this is logarithmic, so these are really many vertices. And here actually you don't see the number of maximal cliques growing exponentially. Like, to me, this could still be polynomial, linear, or depending on the slope or other polynomial, but it doesn't seem to grow exponentially. Of course, here, for when the degree exponent is a bit larger, you do see that it's indeed not growing polynomially, but it still needs quite large. So for here, we would need really large graphs to see that they are not growing linearly, but actually much faster than linearly. And we also showed it like this because we found lower bounds on the number of maximal cliques, but so that would be so asymptotically there's an exponential number of maximal cliques, but there's also a linear term in the number of maximal cliques in most real networks, because real networks may have many vertices of degree 1. And if you are a vertex of degree 1, then the largest clique you are in will always be the single edge, because a vertex of degree 1 cannot be part of a triangle or 4-clique or whatever. And because there's often a linear number of degree 1 vertices, it means that there's also a linear term involved in the number of maximal cliques. Of course, an exponential term in theory should always be larger when a network is large than a linear term. But here it turns out that this linear term actually dominates until a very large graph size. So here we have the model without any geometry. And there we can also see, so here we just have a linear line. And even for networks up until 10 to the 7, this, I see here the plot is not complete, but even for 10 to the power 7, the linear term is larger than the exponential term that we computed as a lower bound. The same here, and also in the model. So this is the model with geometry. There we see here, when you have a very low degree exponent, still it may grow. It's at some point it becomes larger than the linear term, but if the degree exponent is lower, you really need huge network sizes to see that the maximal cliques are not growing exponentially at all. So that sort of explains why the experiments on the real world data could still work, because on real world data, it seems that the number of maximal cliques grow linear. On random graphs, we prove that they grow exponentially, but actually exponentially with apparently a very low growth rate and a very low constant, so that in practice, actually the linear term still dominates. So then one final thing. So we said that, well, in random graphs, you usually have one very large clique minus a matching, which forms very many large maximal cliques. And because of only this very large clique minus a maximum, we have very many maximal cliques. But of course, you could also be interested in smaller maximal cliques. So suppose that we fix some size k. So for example, if k is 3, we would be interested in how many triangles are there that you cannot grow any larger. And it turns out that we can also actually prove how many of those maximal cliques of a fixed size are there. And so it turns out that for any fixed k, so 10, 20, 6, so the graph without geometry has approximately n to the power this weird exponent maximal k cliques. Now, the particular value of this exponent is actually not so important, I would say, but what is important is that here actually nothing depends on k. So it means that asymptotically you see just as many maximal triangles as maximal 4 cliques, as maximal 5 cliques or 10 cliques. Of course, the constant here will be different, but they grow actually the same. And what is also interesting is that this exponent is actually always smaller than 1. So there's fewer than a linear number of small maximal cliques. And we can see it here. So here there's the exponent of the maximal k cliques, where here there's the degree exponent, and we see it is always smaller than 1. So there's always smaller than linear number of k-cliques. And this is actually very different than if you don't look at maximal triangles, but you just count all triangles. Because if you count all triangles, you actually may have more than linear many triangles. And here we also see that for 4 cliques, you actually always have more 4 cliques in inhomogeneous random graphs than 3 cliques, and more 5 cliques than 4 cliques. Whereas if you only look at the maximal ones, you see that they are basically growing at the same speed, and also there's a very low amount of them, as we would actually similarly to what we saw in the real data. Now, what we could also show is that all small maximal k-cliques that you find basically look like this, with very high probability. So they look like this, so they have k-2 nodes of very high degree. So n to the power 1 divided by tau minus 1. That means that these are really the highest degree vertices in your network under our assumptions. And then there's 2 nodes that have this weird degree, so approximately n to the power tau minus 2 divided by tau minus 1. So this is a lower degree. So a maximal k-clique has k-2 hubs. These are connected with probability 1. And then 2 low degrees that make sure that it's actually very unlikely that the clique still grows. Because if you add 1 more edge, it's very unlikely that it connects to both these 2 vertices. And if it doesn't connect even to both these 2, it can of course never form a clique, because to be a clique, it needs to connect to all of those. So if it doesn't even connect to both these 2, then it can already not be a clique. So then we show that actually to be a maximal k-clique, you really need to look like this, otherwise it's actually quite unlikely. So the main conclusion is that exponential bounds in theory can look very linear in practice. Most realistic random graph models contain many maximal cliques, but the practical bounds are still, in practice, if we have our exponential lower bounds, they're still smaller than linear up until a very large amount of nodes. And also that small maximal cliques are very rare. They appear sublinearly many, and they actually also appear in very specific shapes. Now, there's still some problems that we did not manage to solve. So, for example, the what does the maximal k-clique looks like? We solved this for the model without geometry, but for the model with geometry, this seems a bit more tricky. So there is still very interesting to see if something like this would hold as well. And also everything I presented here was lower bound, because we set out to prove that something would grow linearly. And once we had an exponential lower bound, we already figured that getting something linear is impossible, but we didn't actually investigate whether there's also an upper bound. But we do believe that our lower bounds are reasonably close to the maximal, also close, that they should be reasonably close to an upper bound on the number of maximal cliques, but we didn't prove it. So thank you very much.
Thank you, Clara. That was great. So if anybody online has questions, feel free to raise your hand or go ahead and write them in the chat. I can start us off with one that maybe you've heard before, which is there's a lot of network data these days that comes in the form of cliques, as in like group interactions that we will often model now with hypergraphs and simplicial complexes, but it wasn't uncommon even 5 years ago to model this data using pairwise networks. So I wonder if you've investigated, like in the other paper, if any of those network data sets were coming from this kind of data that is inherently clique-like, or if you have expectations about what the behavior should be when you know that the network you've constructed is a bunch of cliques, like collaborations or something like that.
Yeah, so indeed, I would be surprised if there's no collaboration network in there whatsoever. So probably there's at least one or two of them in there that you could say is more likely to be a hypergraph or simplicial complex. But I would, so this then I guess would say that I guess like if you have a large number of if you have a clique, this clique minus a matching, I guess that would mean that one specific node is in many, like really many hyper edges, so that the hyper edge degrees would be very large for specific nodes. Yeah, I guess.
Yeah, which I guess you would kind of expect, right? So then the fact that all of these real networks didn't have this behavior might be surprising, I guess. Yeah.
Yeah, indeed. So there's large, but there would be like large number. This thing would actually then mean that there would be sort of a large number of like almost like very similar hyper edges, which then exclude one node but include another node.
Yeah, okay. Yeah, that's less likely to happen. Yeah, there will be more.
Yeah, so but maybe that is also why it's this doesn't happen in practice, and why in practice it's more linear, and why in our theoretical analysis this can happen, and then it's exponential.
Thanks. Yeah. Rohit has a question. I'll try to lift up.
Thanks. A quick question. I hope you can hear. Can you hear me, or should I come closer, maybe to the mic?
Come closer.
I couldn't hear it, sorry.
Yeah, he'll come closer.
Yeah. I hope this is better.
Yes.
Thanks for the talk. I had a quick question about the definition of maximal clique is rather strict, right? If I'm more interested in looking for, let's say, just generally dense areas in my graph, is it possible to maybe relax the definition of maximal clique a little bit? And how would you expect perhaps the bounds that you find both in theory and in practice to change if I'm happier with a more relaxed definition?
Yes, so I think indeed, so I think this makes a lot of difference, because indeed if you relax it a bit, I mean, I don't know how to do it, because maybe you could say like if the clique is very large, so maybe for a very small one, so for triangles you really do want a clique, because having a triangle or a wedge, I think that does make a difference. But you could say like if the clique is very large compared to the network, then maybe you want the proportion of your network to be connected to be close to 1.
Right.
Or 1 minus a very small order term. And in that case, I think you would probably have a linear number, because we really show that there's very large cliques minus a matching. And that is already many maximal cliques. But if you say, oh, I'm quite happy with a clique minus a matching, I already consider this to be a clique, then actually you would just have a few of them, I think.
Okay.
So that it really makes a very strong difference, I think. So yeah.
All right. Thanks.
Great. I don't see anything in the chat. Any other questions, either in person or online? Not seeing any. So in that case, thank you very much again, Clara, for coming. Let's thank Clara again. And yeah, so this is our last seminar of this term. So we'll be back next term, which I didn't look up the date, but mid-January. Yeah. So thanks again, Clara, and thanks everyone for coming. And we'll see you next year.